All right. So actually, we are going to see that questions which are under the speed control. Yeah, there's so many questions that you are going to have carrying a lot of marks. So they're just stages and things that you need whenever you are to calculate anything about the speed control. Remember, there are two conditions where you need to understand. The first condition, which is the original, where we are assuming that at original conditions, the motor runs at a normal speed while producing 100% torque. That is at normal mode. Then when it is at the final condition, there are so many things that will change. One, the current that is being drawn from the supply, which is the current taken from the supply, it will change from current I1 to current I2. The speed also changes. If there is a speed on the first condition, we are going to have the speed of the second condition, which is the final condition. The torque on its own changes from T1 to T2. The induced EMF changes from E1 to E2. All these are going to change, except for what? The voltage taken from the supply, the field, which is the shunt field resistance, the armature current. These three are not going to change. But there will be a condition. So whenever you answer this type of a question, you need to consider, read the question that you're given carefully. Draw your diagrams, then use the formula for the speed control, which is any of this part. So I'm going to explain these formulas and other things that you also need. There are so many things that you need. Not so many things, but just one or two that you need. So let us consider our question there, what we are given. We were given a shunt wound DC motor. So this is a DC motor that you're given, draws 30 amps, which is the load current, from a 250 volt. So it draws 30 amps, which means the supply. So before that, you do not know what's going to happen. So you just know, okay, this is the current that is being drawn. Then after you read this information, you're going to come to this statement where they are saying there is a 30% torque reduction when a 1,2 ohm, resistor is connected in series to the armature. That condition tells you that now you're working with the speed control. There is an additional resistance. Where is it connected? You must be careful. Where is it connected? Is it connected to the shunt field? Is it connected to the armature? So to the armature, it's connected in series to the armature. So that makes us to say we have got two conditions, the first and the final condition. The original condition from the current that you are given, we have got the load current of 30 amps that you are given there from the supply of 250 volts. All right. Then you are given the resistances of the armature and the shunt windings are 0,2. So this is 0,2 for the armature. So we've got the armature resistance 0,2. Then the shunt field, meaning to say we've got the resistance that is affecting our shunt field in this case. So you can just write as RF for the shunt field resistance. So you can even write RF1. All right, then this is the current that is going to flow in the field, which is the shunt field. Remember, from the supply, another current is taken by the shunt field. Another current is taken to the armature. So you're going to have the armature current 1, the power output. And as we know, there must be a generated EMF between this part of our armature. So we are going to have the generated EMF, which is actually the back EMF, because we're talking about a motor there. Okay. Given the full load speed, the full load, at full load, that's at the original condition, at full load, the speed is 950. So we're given the initial at the full load N1, which is 950 revolutions per minute. Then the question there was that there is a 30% torque reduction. All right, so this is what you're going to do in exam whenever you're given this part of the torque. I think, all right, so these are actually the procedures that you need whenever you attempt a question on speed control. Like I said, reading of the question, then you're going to use the formula, this and that. So you're going to talk about that. But I wanted you to have this part. It is important that you understand this when dealing with the torque. Note that the torque formula that we have there contains 6 variables to eliminate, that is to get rid or reduce the number of unknowns. Consider the interpretations of questions below. If the question reads, we are given, these are the condition, your typical exam questions, how they're going to give you. Assume that the torque remains constant, that is, or unchanged or unaltered. It means T2 is equal to T1. Remember, there is a change that is going to happen in the torque. Like I explained, the torque is going to change from T1 to T2. But when they are saying it remains constant or unchanged or unaltered, that means T2 and T1 are the same. That's a condition that you have there. Another condition is they can tell you, assume that the torque is reduced to 90% of the full load torque. It is reduced to 90% off. At full load, the torque there is T1. So it means your T2 is going to be 90% of T1, which is 0.9 T1. If it is 70%, 0.7 of that, and so on and so on. That is the idea of the question. Assume that the torque reduced by 20%. If you reduce maybe by 20% or maybe by 30%. So it means T2 is going to be 100% minus the 30% that you are given of T1. If it is 20%, 100 minus 20%. Okay? Assume that the torque is increased by 25%. This time it's increased. So from 100% increase, you add. So it will be 100 plus. So these are the conditions. Then assume that the torque is proportional to the speed. It means our torque is proportional to the speed. Then these are the formulas that we are going to consider in our calculations. So you must at least have this in mind whenever you're answering these typical questions. So on our typical question that we have, if we are to consider this properly, they say that, we want to go back to that part here. They say that here, and I want you to see this. They are saying there is 30% torque reduction. There is 30% torque reduction. So it is the same condition as this one that we are given here, which states that assume that the torque is reduced by a certain percentage. So T2 is going to be 100 minus that percentage reduction. Remember, they're saying it is reduced. There's a reduction. So our T2 is going to be 100% minus, because there's a reduction of 30%, you subtract. So that is 100 minus 30% of what? Of T1. So 100 minus 30 is going to give you a 70%. That's 70% of T1, meaning to say as a decimal, 0.7 of T1. So this is a condition or a relationship that you're going to take into consideration between the torque of T2 and that of T1. That T2 is 0.7 T1. It's a condition that you are taking from this part that you're given. So you use any of those conditions. You're going to be given any one. Is it an increase? Is it a reduction? Is it remaining unaltered, unchanged? All right. So when this is happening, they are saying when a 1,2 ohm resistor is connected, where is it connected? In series to the armature. Before, we just had our armature as it is, with its armature resistance of 0.2. This is the part of the armature. But now they're saying we connected a resistor in series. That's an additional resistor in series to the armature, not to the field, but to the armature. So it's a condition that you need to consider. So we are going to add a series resistor there to the armature. Maybe it is connected in series to the shunt. You're going to connect it there. But in this case, it was connected to the armature. So you work with the condition that you're given. It's not always that it is going to be connected to the armature. Sometimes they are going to connect. They're going to tell you that it is connected to the shunt field. You connect it in series to the, meaning to say it's a condition on its own. You work with that. That's the new condition. So the new condition is that we connected a resistor in series to the armature. So when we connected this, it is going to affect a lot of things. I talked about this from the supply current. It is going to be affected. The armature current, it is going to be affected. The generated EMF on its own, because there we are going to have the first one, and here we're going to have the second one. Everything that we have on this part, except for this voltage and your RF, those ones will remain the same, and even your armature resistance, only that there is an additional there. So you must be careful. So we saw that from this we are given, let us take this. They are saying calculate the new speed of the motor. So sometimes they'll ask you to calculate another thing on its own. So there it is to calculate the new speed, meaning to say we need N2, because already we have got N1 from the initial or from our original condition. Assuming that the field coils are unsaturated. So meaning to say, in this condition, we're just going to consider our flux to be proportional to the what? To the field current. All right. This is it. I want us to go back here. The procedure to solve speed control problems. We saw that you're going to need the diagrams as we have there. Read the question carefully. I mentioned about this. Then you draw your two large full labeled circuit diagrams, because there is original and final. So they're supposed to be two diagrams. Write down the main speed control formula, which is the one that we are going to use to find out what is it that is to be calculated. That is about the speed control, which is this part of your formula sheet. In your formula sheet, they gave you this part this way. This is your formula sheet here. What does it mean? The K is a constant, so it's just not there, this one. And on a condition like this, the flux 1 will be equal to the flux 2. It means we just left with N1 over N2. Know your formulas, how to attempt with these formulas. Also for torque, the K and the K are the same. So they will cancel these two. They're the same. It's just like it's not there. It's just like it's not there. So we are given from our formula sheet in terms of the flux. So I'm going to write this in terms of the flux. They are saying, this is the way here. I want us to be together. Now we are answering the question. E1, which is the generated from the original, is equal to, they were given the K and the K are constant, so those two will cancel. This is what you have there, flux 2 over N2. On a condition that our flux is proportional to the field current, that is where we end up with the field current with the constant, but the constant is the same. So it means we can even replace, in place of the flux, we can replace it with the field current. So instead of this, we can use field current 1 times N1. The same thing, we can replace this with field current also 2 times N2. It's one and the same thing. So the question is, what are we having? What are we asked to calculate? We are asked, guys, let us consider this. Let's be together. We want to be together on this question. This is the flux. In this case, we do not have anything related. But as you can see, the field current, there is a higher opportunity of calculating the field current. Remember your shunt current. The field current there is the shunt current. Consider when we're dealing with a shunt motor, how are you calculating the shunt current? Okay, you still need that information of your shunt motor, the same way as if you're working with a series motor. So each and every part has got a part that you're going to refer back to. So remember that when you were working with your shunt motor, you are considering the voltage over R shunt. But now we're just considering as RF. So instead, we're just going to have as I1, IF1, which is the field current, is equal to the voltage over the shunt field, which is now referred as RF1. Just one and the same thing. So meaning to say the best formula to consider, it is this to this, not this one, because we do not have the flux totally there. Totally, we do not have. But because flux is proportional to the field current, we can relate it in terms of what? In terms of the field current. It's not always when this field current is equal to this. All right? It's not always when it is equal. But on a condition like what we are given, on this condition, if we are to consider it, what affects, I want you to be careful, because some of these questions, it's not because we do not know this, or it's just we had this before in our info, but just that revisions and so forth. We are talking about the field current here. If we are to consider, because of this condition, that there's nothing that has changed along the field from the original to the final, by this default, we are going to see that the first field current is going to be equal to the second field current, which is the same condition that our flux 1 is equal to flux 2. Guys, you must be careful. It's either you are going to calculate these field current. I'm not saying it's wrong. But on this condition that we have here, on these ones, they're the same. There's nothing is affected here, the part of the field. It is the part of the armature here which is being affected. This affects the generated EMF because the EMF is the one that is generated from where? From the armature. But the field is not affected. All right. Anyways, let us calculate because it might be like something else that does not exist. Let us just do this so that you see what I'm trying to say. The field current, remember I said this is same as the shunt current. Remember from your shunt motor, the shunt current was equal to the voltage over R shunt, which is in this case our R field. So the voltage is the same, does not change, 250. In the field, there is a 150 volt, a 150 ohm resistance. So this was going to give us what? The current of the field, which if we're to calculate this properly, because each and every part that you're given, it is affected. So this was going to give us something like 1,667 amps. This is the field current from the original circuit. Just because there is nothing that happened along the field in the final, because we did not add a resistor there. We added a resistor to the armature. So it doesn't affect the field. I want you to see this. V over, in this case, what are we having? There's just one resistor, which is our shunt resistor, which is our field resistor too. The voltage is unaltered, is just the same, 250 over the same resistance of 150. So in another case, they will give you a it's from the condition. If they say there is a resistor added to the field in series like this will be totally wrong. You work with the condition that you're given. The resistor is on the armature, not the field. So therefore, these two will be the same, 1,667 amps. So if you were to note this earlier on, let's say you realized this earlier on, it means you're not going to waste much time calculating this. Because on this formula, you can also make alterations. Okay, E1 over E2 is equal to, this is what we are supposed to have in the original sense. This is what you are supposed to have. But because these two are the same, you're just going to cancel. Meaning to say we are left with N1 over N2. You are not going to waste much time of this. But in any case that you did not realize this, it's not a problem. You just substitute, then you see, oh, this is one and the same thing. It's one and the same thing. So we have got these two guys. They are already there. These are the ones that we are seeing here. The question that we are seeing, remember, it is to calculate N2. So we are going to circle what we need to calculate, which is our N2. What about N1? It's already there. N1, that is the speed. E1, which is the generated EMF, we do not have this one. We do not have. E2, we do not have. So we are forced now to calculate these two. So I'm not going to consider, you can even, there is any way that you want. Consider this to this or this, whatever that you want. But we do not have E1, we do not have E2. What do these two represent? The generated EMF. A motor, that is the back EMF. From the specific EMF equation, we do understand that, all right, let me bring you back from your formula sheet. The specific EMF equation allows us to play around. We can play around the voltage, armature current, and what is part of the armature. Like I said, the plus there being for the generator, but in this case, we are dealing with a motor. So it means we are going to use E, which is equal to V minus IA times RAC, which is everything as part of the armature circuit. So calculating E1, it means we are going to use V1, which does not change, V and it's the same. So we're going to need armature current from the original circuit, the armature resistance or the armature circuit resistance of the original circuit. Everything there we have. So you can calculate E1. The voltage of 250 we are given minus the armature current. All right, so the armature current, let us consider our diagram. If you are to consider your diagram, you are going to see that there is no armature current, but remember you calculated the series field, which is our shunt field, this shunt field current. So you can take advantage of that. Remember, on a shunt motor. So there we are now forced to have this in our calculation, okay? So let us calculate our armature current of the original circuit, which is armature current 1. This is the same, guys. Remember your shunt motor. From the Kirchhoff's law, the armature current, we do understand this load current 1 is equal to the field current 1 plus the armature current 1. So as we need the armature current 1, this one. So you're going to make it the subject, take this to the other side, that will subtract. So if you subtract this, that means our armature current 1 is equal to the difference, which is the load current 1 minus the field current 1 from the first circuit that you're given. So it is an advantage here because we have got the load current and also we have got the field current from what we calculated. 30 amps, which is our load current. So that will be 30 amps minus the 1,667 amps, which is from our field current of the first circuit, which is our original circuit. So that was going to give us the armature current of the first circuit, which is the original circuit, and that was going to be 28,333 amps. Remember, this is current. All right, so let us just put this one aside. So you have to be careful. Calculate this, you move on, you calculate this one, you just put it aside. So we have got this armature current 1, which is missing here, so that we can calculate our generated EMF from the original circuit. So that's it. Our armature current from the first circuit, that's 28.33. So let us just substitute here. So this is 28,333 times. This is the resistance of the armature circuit, everything that is affecting the armature of the first circuit, of the original circuit. There is only the armature resistance, nothing is there. There is only the armature resistance there of 0,2. So that's it. This from 250 was going to give us the generated EMF, which is 244,333 volts. That is, okay, we calculated something. So this is what you're going to do each and every part. So we have got E1 now. We need E2. So in the same manner or in the same sense, E2 is of the second, the final. Remember, it changed. Generated EMF here, there is a generated EMF there. So we are supposed to consider the final. So in this case, I'm just gonna take off this, guys. We're just gonna allow me to do so that we just utilize this space here. Remember, these two, we said they are the same. But now let us consider to say you wanted to calculate E2, which is the generated EMF of the origin of the final, circuit, which is the one that we are given after the changes. Okay, you think of to say, okay, let me take this one into consideration to say I want to take this. E2 is equal to V minus, you're going to have the armature current of the second times everything that you are given in the armature circuit, the resistance of the armature, meaning to say what affects the armature. There is a 1,2, an additional resistor, and the 0,2. So meaning to say our RAC in this case was going to be this additional resistor, we can just call it RX, plus the armature resistance of 0, which was fine. But the question is, on this formula, are we having I2? I mean the armature current 2. We do not have this one, the armature current 2. Okay, so this is not there. This we have it. We want to calculate E2. Definitely, we cannot have what we want to calculate because that is what you want to calculate. So you can just give a benefit of doubt for now. Let us move on to current, which is the armature current. We were supposed to calculate this armature current from the supply, the series, the shunt field, which we have, but the supply this time we do not have. Like what we had previously, there was a supply there. So we took advantage of the supply current that we are given here to say the supply current is equal to the field current plus the armature current. So you can make the armature current the subject. But this way now we are limited because we do not have this supply. And it's difficult for us to have that supply for now. So meaning to say we are going to have two unknown values on one formula. And that's complicating our formula. So this is complicated for now. So let's think along what we have, because there is a condition here that we are given about the torque. What is it that we can have? Because what we need is the armature current. So from the load current, let's forget about that because there are going to be two unknown values. So the load current, just forget about that. So think of another way of having this same armature current that we could have calculated using the load current. Let's go back to our formulas. Because of the torque that we have, we also have a relationship of the torque also on our speed control. T1 over T2 is equal to this. There is a relationship that we are given about the torque. So we can take advantage of that because there's a relationship there. So in this case, from the torque, think of that. From T, we can calculate this armature current. So the relationship is stating that, all right, so remember we talked about the condition of our flux being proportional to the final current, this and that. So you're going to see that T1 over T2 is going to be equal to the armature current 1 times the field, which is the shunt field 1. Then we're going to have the armature current 2 times the field current 2, because flux and field current, they are proportional. But because we saw before, remember we calculated these two, the field current 1 and the field current 2, and we saw that they were the same, which was something like 1,667 amps. We remember we calculated this before. So it simply means these two, if they are the same, we can even remove it from our formula because they are the same. So we are just left with T1 over T2 is equal to armature current 1 over armature current 2. Remember, what you need to calculate is armature current 2. This is what is missing or what we need on our formula, armature current 2. T1 over T2, we do not have T1, but we are given that T2 is equal to 0,7 T1. Remember from that reduction percentage that we talked about before. So we can leave T1 as it is, but we write T2 in terms of T1. So T2 in terms of T1, it's 0.7 T1. So definitely these two will cancel. All right. The armature current 1, we calculated this before. Remember our armature current 1 from the original circuit. We got our armature current 1 there. It was 28.333 and so on. So we have got the armature current 1, which is 28.333 over the armature current 2, which is the one that we need here. So we're going to calculate this. So like I said, here, because T1 and T1 are the same, so they can cancel. You remain with a 1 there. Cross multiply to find I2. That is armature current 2, That is 1 times armature current 2. Then there you cross multiply 0.7 multiplies 28.333 like that. So that will be 0.7. 0.7 times 28.333 like that. That was going to give us 19.833 amps as your armature current for the second or for the final condition. Why are we in need of the armature current? It is because we need the generated EMF. So just allow me to remove this again. So we're going to take this. Remember, don't forget this answer. 19.833 for the armature current of the second circuit. With the armature current that we calculated, now we can calculate our E2. V is not going to change to 150 for the final condition. The armature current is the one that we just calculated now. Remember, we just calculated this and we said it's 19.833. Then this circuit that we are seeing on the armature, there are two things to be considered there. The additional resistor and the armature resistor, because this is the part of the armature circuit. There is a series resistor. Remember, in series you add. So you were going to add these two, the additional resistor to the armature resistor. The additional resistor being 1.2 ohms. The armature resistance originally it was 0.2. So that was going to give us E2 because there is an additional resistor. It means your RAC is going to be affected. It's in series, so you have to add that one. So this was going to give us 222.234 volts. This is the generated EMF or the back EMF of the final condition. On this formula that we are given here, that we said we will need to use to find whatever that you're given, we can see that everything is now there. E is now A1 is E2. Everything is now there. What we need is N2. So we're going to make it the subject. So you write down this formula first. Then you have to figure out what is missing in the formula. What is it that is missing from the formula? Then you calculate those things. We need to find N2, remember? And we saw that these two are the same from our calculation. There's no need for us to substitute. You can substitute, it's fine. But we saw that we calculated these two. They gave us the same answer, 1.667. So you can even ignore that because these two are the same. So just substitute, calculate your E2, your N2, this one. You have got everything. E1, you calculated this, 244,333 over E2, which is the one that we just calculated now. Our E2, which is 222,234. 22,234 is equal to N1. Already we have this one. Remember, we are given the speed initially, it was 950 revs per minute at full load, meaning to say at original condition, the speed was 950 over what? N2, which is the speed that you are being asked to calculate. Now you can calculate your speed. You can even make it the subject before you do this. It's up to you. You can substitute like this. It's up to you. Cross multiply, divide. So this will be 244,33, and 2 is equal to 950 times 222,234. So definitely you're going to divide by this, both sides. So that was it. You have got the speed, which is affecting our motor in the final part. And this was going to be 864,076. Speed measured in revs per minute. We were given before the other speed in revs per minute. So definitely this one must be also in revs per minute. So speed control calculations, we are not yet done. Like I said, each question is on its own. How we answer this question, how we went through to calculate these might differ because of the condition that you are given. So you must consider the condition carefully. The conditions that you are given are the ones that will affect the final diagram. And this final diagram affects your calculations of the final circuit, which is the final field current, if it is to be calculated, the generated EMF of the final circuit. It is because of the condition that you're given. So you have to do as many questions so that you figure out how do they ask questions on speed control, because it differs, but the formulas, one and the same, considering what we talked about here from our equation, which is the generated EMF and speed control. We can assume and work with these conditions, and also consider what I said about the torque before. So these are the questions till we meet again.